In 2002, a geology student walking through an open-pit coal mine in northern Colombia picked up what looked like a fossilized tree branch. It wasn't a branch, it was a rib, and it belonged to an animal that, once fully reconstructed years later, would turn out to be the single largest snake ever known to have existed, an animal so large that its body was too wide to fit through a standard doorway. That snake is Titanoboa, and for the better part of 2 decades, it's held the undisputed title of biggest snake in the fossil record, a title that's shifted and sharpened considerably as new research and new fossils have accumulated. This is the story of how scientists figured out just how big Titanoboa actually was, why a second competing giant turned up on the opposite side of the planet, and what both animals reveal about a period in Earth's history when reptiles briefly got to be the largest predators on land. The Terrijon mine, where that first fossil turned up, is one of the largest open-pit coal operations in the world, and the layer of rock being excavated dates back to the Paleocene epoch, a roughly 10 million year stretch immediately following the extinction of the dinosaurs, somewhere between 58 and 60 million years ago. Before this discovery, almost nothing was known about tropical ecosystems from that specific window of time, since fossils from tropical regions tend to degrade faster and are considerably harder to find than fossils from cooler, drier environments. What paleontologists eventually pieced together, digging through the mine over the following years, was evidence of an ancient tropical rainforest, one of the earliest known examples of the kind of ecosystem that still covers much of the Amazon basin today. And scattered through that ancient forest floor were the remains of an enormous snake, described formally by a research team led by paleontologist Jonathan Block of the Florida Museum of Natural History, working with Carlos Jaramillo of the Smithsonian Tropical Research Institute and Jason Head, then at the University of Toronto, Mississauga. They named it Titanoboa cerrejonensis, Titanic boa of Cerrejon, and the name turned out to be entirely earned. Researchers ultimately recovered partial remains from roughly 30 individual animals, primarily vertebrae and ribs, which is actually a reasonably substantial sample size by the standards of large extinct reptiles. Snake vertebrae, it turns out, are unusually useful for size reconstruction. Their dimensions scale in a fairly predictable measurable relationship with an animal's overall body length and mass in living snakes, which means researchers can take a fossilized vertebra, compare its size against that same relationship in modern boas and pythons, and back calculate a reasonably confident estimate of how large the original animal must have been, even without a single complete skeleton to work from directly. The numbers that came out of that analysis were, by any reasonable standard, startling. Adult Titanoboa individuals are estimated to have reached somewhere around 13 meters in length, roughly 42 to 43 feet, with some later modeling work suggesting the true figure might run closer to 14. 6 meters once additional variables were factored in, a number that's since been commonly rounded up to around 15 meters in some later popular accounts. Mass estimates put a fully grown individual at somewhere around 1,135 kilograms, roughly 25 metric tons, with some estimates running as high as 1,140 kilograms. To put that in more tangible terms, researchers involved in the original description noted that Titanoboa's body was thick enough that, at its widest point, roughly a meter across, it would have had genuine difficulty fitting through a standard doorway. Jason Head, the paper's senior author, put it memorably at the time. If the snake were moving down a hallway and decided to come into someone's office, its own girth would force it to squeeze through the doorframe. Bloch, separately, compared its overall length to that of Sue, the famous Tyrannosaurus rex skeleton on display at Chicago's Field Museum, essentially the length of a dinosaur wearing the body of a snake. By comparison, the largest living snakes on Earth today, reticulated pythons and green anacondas, top out at somewhere around 9 to 10 meters in exceptional, well-documented individual cases, and average considerably smaller than that. Titanoboa wasn't simply bigger than any snake alive today. It was operating on a scale that modern snakes, constrained by modern climate and modern ecological pressures, simply don't reach anymore. The obvious follow-up question is why a snake this size existed at all, and the answer connects directly to something snakes, as cold-blooded animals, depend on in a way warm-blooded mammals and birds don't: ambient environmental heat. Snakes are ectotherms, meaning they can't generate their own internal body heat the way mammals do. Instead, their body temperature, and by extension, their metabolic rate, activity level, and growth potential, is directly regulated by the temperature of their surrounding environment. In a cooler climate, there's a hard ceiling on how large a cold-blooded animal can practically grow, since a bigger body requires more sustained warmth to keep its metabolism functioning at a level that supports that size. The Paleocene epoch, when Titanoboa lived, was significantly warmer than today's climate, part of a broader greenhouse period in Earth's history with substantially higher average global temperatures than the modern world. Researchers working on Titanoboa have used the snake's own size, in fact, as an indirect proxy for reconstructing just how warm the tropical climate of that period actually was, reasoning backward from body size to the minimum ambient temperature that would have been necessary to sustain a cold-blooded animal that large. That analysis suggested average tropical temperatures in the region during Titanoboa's lifetime may have run several degrees warmer than equivalent tropical regions do today, a genuinely useful data point for climate scientists trying to reconstruct ancient global temperature patterns, entirely independent of the snake's own biological interest. There's also a second, more ecological factor at play, one that has less to do with temperature and more to do with opportunity. Titanoboa lived in the immediate aftermath of the mass extinction that wiped out the non-avian dinosaurs, a period when many of the largest predatory niches on Earth had suddenly been vacated. With large terrestrial predators largely absent from the landscape, at least temporarily, an unusually large reptile moving into an apex predator role had considerably more room to grow and less competition to contend with than would have been available during the Mesozoic, when dinosaurs still dominated every major size class. Reconstructing Titanoboa's likely diet and hunting behavior has relied on a combination of anatomical inference and comparison with living relatives. Based on skull anatomy, researchers have suggested Titanoboa was likely primarily piscivorous, meaning fish made up a significant portion of its diet, which fits neatly with evidence that the Ceredigion region was a swampy, low-lying tropical environment threaded with rivers and wetlands, exactly the kind of habitat that would have supported large fish populations. That doesn't mean fish were the only thing on the menu. Given its sheer size, researchers have reasonably speculated that Titanoboa was also capable of taking considerably larger prey, up to and including the crocodilians that shared its ecosystem, several species of which have been recovered from the same fossil beds. Like modern boas, pythons, and anacondas, Titanoboa almost certainly hunted through constriction rather than venom, an ambush predator that would have relied on stealth and raw physical strength rather than speed or pursuit, coiling around prey and using its considerable body mass to subdue it before swallowing it whole, exactly the strategy its much smaller modern relatives still use today. More recent modeling work, drawing directly on the biology of living green anacondas as a comparative framework, has pushed these estimates even further, suggesting that a fully grown Titanoboa may have been capable of consuming prey items weighing several hundred kilograms in a single meal, with some theoretical maximum estimates running well over a ton for an exceptionally large feeding event, though these figures come with considerably more uncertainty than the core size estimates themselves, since they rely on extrapolating feeding behavior across an enormous size gap between Titanoboa and its modern relatives. For close to 2 decades, Titanoboa's size record stood essentially unchallenged. That changed in April 2024, when a research team led by paleontologists Debajit Datta and Sunil Bajpai, both at the Indian Institute of Technology, Roorkee, published a description of an entirely separate giant snake species in the journal Scientific Reports, one that had actually been sitting misidentified in a museum collection for nearly 2 decades before anyone realized what it actually was. The fossil material, 27 vertebrae, several of them still articulated in their original anatomical sequence, had been collected back in 2005 from the Panandro lignite mine in the Kutch district of Gujarat, western India. At the time, the bones were tentatively identified as belonging to a large crocodilian, a reasonable enough guess given their size, and they sat unstudied in that classification for the better part of 2 decades, until Datta and Bajpai undertook a detailed re-examination and realized the material actually belonged to an enormous, previously unknown snake instead. They named the new species Vasuki indicus, after Vasuki, the mythological serpent king depicted coiled around the neck of the Hindu deity Shiva, paired with a species name acknowledging the country where it was found. Dating placed the fossils at approximately 47 million years old, during the Middle Eocene epoch, meaningfully younger than Titanoboa, but still comfortably within that same broader window of unusually warm, post-dinosaur global climate. Using the same basic method Bloch's team had applied to Titanoboa, comparing the size and proportions of the recovered vertebrae against a range of living and extinct snake relatives, Datta and Bajpai calculated a length estimate for Vasuki indicus of somewhere between 10, 9, and 15. 2 meters, roughly 36 to 50 feet, putting it in the same general size class as Titanoboa, and, depending on where within that estimated range the true figure actually fell, potentially even longer. Weight estimates put a fully grown individual at somewhere in the neighborhood of a metric ton, broadly comparable to Titanoboa's own estimated mass. Bajpai himself has been notably careful about the direct comparison between the two animals, pointing out that while the estimated body lengths are broadly comparable, Titanoboa's individual vertebrae are somewhat larger than Vasuki's, which leaves open the real possibility that Titanoboa was more massive or thicker-bodied, even if the two animals reached similar overall lengths. Without more complete skeletal material for either species, that particular question, which animal was genuinely larger once total body mass rather than length alone is taken into account, remains formally unresolved. What makes Vasuki indicus scientifically interesting isn't just its size, it's its family tree. Titanoboa belongs to the boid lineage, the same broader group that includes modern boas and anacondas. Vasuki, by contrast, belongs to an entirely different and now extinct family called Madtsoiidae, a group of snakes that first appeared much earlier, during the age of dinosaurs, and managed to survive well past the extinction event that ended it, persisting for millions of years afterward in isolated pockets before eventually dying out entirely. Based on its build, inferred from the thick, cylindrical proportions of its vertebrae, researchers have suggested Vasuki was likely a slow-moving, heavily built ambush predator, broadly similar in ecological role to Titanoboa, despite the two animals belonging to entirely separate evolutionary lineages, evolving comparable giant body plans independently, an example of what biologists call convergent evolution, separate lineages arriving at similar solutions to similar ecological opportunities. The discovery also carries broader implications for how this particular family of snakes moved around the ancient world. Data and Bajpai's analysis placed Vasuki within a distinct evolutionary clade alongside other giant Madtsoiid species previously found in India and North Africa, suggesting that this entire lineage of giant snakes may have originated specifically in India and then dispersed outward from there, potentially spreading through southern Europe and into Africa during the warm climate window of the Eocene, tracing a migration pattern connected to the ancient supercontinent breakup that separated the landmasses making up modern-day India, Africa, and Europe. It's worth pausing here on something both research teams have been genuinely upfront about. These size estimates, however carefully calculated, come with real uncertainty attached, and treating them as settled, exact figures oversells what the fossil evidence can actually support. Neither Titanoboa nor Vasuki indicus is known from a complete skeleton. Every length and mass estimate for both animals is derived by comparing fossilized vertebrae against the vertebra-to-body length relationship documented in living snakes, then scaling that relationship up to a size range far beyond anything that relationship has ever actually been tested against in a living animal. That's not a flaw in the method, it's simply the best tool available given what's actually been recovered, but it does mean the resulting numbers are genuinely estimates with a real margin of error, not precise measurements. Data and Bajpai themselves explicitly cautioned, in their original publication, that their length estimates for Vasuki should be treated with appropriate caution, precisely because they lack a complete specimen to confirm the extrapolation against. That uncertainty is part of why both animals are typically described with a size range rather than a single fixed number, Titanoboa somewhere around 12, 8 to 14. 6 meters depending on which specific modeling approach is used, Vasuki somewhere between roughly 11 and 15 meters. The honest scientific position is that both animals were genuinely enormous, comfortably larger than any snake alive today, and that pinning down which one holds the technical size record, or by how much, will likely require the discovery of more complete fossil material for one or both species before that question can be answered with real confidence. If the climate conditions that allowed Titanoboa and Vasuki to reach these sizes existed for millions of years, an obvious question follows. Why don't giant snakes exist today on a planet that, however concerning current warming trends may be, hasn't been anywhere near as consistently hot as the Paleocene and Eocene were during the height of these animals' existence? Part of the answer is simply climate. Global average temperatures have cooled substantially since the Eocene, and modern tropical regions, while still warm by any everyday standard, don't sustain the kind of sustained, elevated ambient heat that cold-blooded reptiles would need to support body sizes in the Titanoboa-Vasuki range. As global temperatures gradually declined over tens of millions of years following the Eocene, the physiological ceiling on maximum snake body size would have declined right along with it. The other part of the answer is ecological competition. Both Titanoboa and Vasuki lived during a specific window when large mammalian predators hadn't yet fully filled the apex predator niches left vacant by the dinosaurs' extinction. As mammals diversified and grew larger over the following tens of millions of years, eventually producing the large predatory carnivores that dominate terrestrial ecosystems today, the ecological opportunity that had allowed giant reptiles to claim apex predator status largely closed. Modern giant snakes, reticulated pythons, green anacondas, and their relatives still occupy a genuinely formidable ecological niche, but they're doing so in direct competition with large mammalian predators that simply didn't exist in anything like their modern form during Titanoboa's and Vasuki's respective heydays. The Titanoboa story didn't begin with a dramatic, single moment of discovery. It unfolded slowly, over years, through the unglamorous, methodical work that defines most real paleontology. The Carajan mine had already been under commercial excavation for years before researchers started paying close attention to the fossil material regularly turning up alongside the coal. The 2002 discovery of a fossilized leaf, rather than any bone, was actually what first drew paleontological attention to the site, since that leaf indicated the rock layer being mined dated to the Paleocene, a period from which almost no tropical fossil material had ever been recovered anywhere in the world. That single leaf effectively told researchers they'd stumbled onto a genuinely rare window into an almost entirely undocumented ancient ecosystem, and it's what motivated the more systematic fossil collection effort that followed over the next several years. The snake vertebrae themselves turned up gradually, mixed in among a much larger haul of Paleocene fossil material, including ancient turtles, crocodilians, and plant remains, none of which initially stood out as especially unusual on their own. It was only once researchers had accumulated enough individual vertebrae and started directly comparing their size against the equivalent vertebrae from modern boas and anacondas that the true scale of what they were looking at became clear. Bloch has described the moment of realization less as a single dramatic reveal and more as a gradually dawning recognition. As vertebra after vertebra kept turning up larger than anything in the comparative collection they were measuring against. That slow, cumulative style of discovery is actually fairly typical for major paleontological finds, and it stands in useful contrast to the popular image of a single perfectly preserved skeleton being pulled dramatically from the rock in one afternoon. Real fossil assemblages, particularly from tropical environments where preservation conditions are generally poor, tend to accumulate in fragments over years, across multiple field seasons, with the full picture only emerging once enough individual pieces have been collected, measured, and cross-referenced against each other. One of the more genuinely difficult questions facing researchers studying Titanoboa is reconstructing its growth biology. How quickly did a hatchling snake actually reach a body size measured in tons? And what did that growth curve imply about its early life? Researchers working from comparisons with living anacondas, currently the closest reasonable living analog in terms of general body plan and aquatic ambush predator lifestyle, have modeled Titanoboa's likely growth trajectory using the same kind of scaling relationships applied to its overall size estimates. The modeling suggests hatchling Titanoboa individuals would have emerged at a modest size, somewhere in the range of roughly 2 meters, genuinely large by the standards of a newborn animal, but still a tiny fraction of the length an adult would eventually reach. From there, sustained growth over multiple years, aided by the abundant warmth and rich food resources of a tropical Paleocene wetland, would have been necessary to reach full adult size. That extended juvenile period carries its own set of ecological implications. A young, still growing Titanoboa, even at several meters in length, would have faced meaningfully different risks and opportunities than a fully grown adult, likely occupying a different ecological role, hunting smaller prey and facing its own predation risk from other animals in the same ecosystem, before eventually growing large enough to become one of the dominant predators in its environment outright. Some researchers modeling this growth pattern have suggested that Titanoboa's reproductive strategy likely involved relatively few offspring per clutch, compared to what a simple size-based extrapolation from smaller snakes might initially suggest, reasoning that an animal investing this much biological resource into an unusually large body size would correspondingly need to invest more per individual offspring to give each one a realistic chance of surviving to adulthood, a pattern that broadly mirrors what's observed in large modern anacondas today. Both Titanoboa and Vasuki indicus generated a level of public attention considerably beyond what most paleontological discoveries typically receive, and that attention says something useful about why stories like these resonate the way they do. Titanoboa's formal unveiling in 2009 came with an unusually vivid, tangible hook for public audiences, a full-scale physical reconstruction of the animal, built and displayed to give people a genuine, visceral sense of just how large the snake actually was, since verbal descriptions and measurements alone tend to undersell an animal of this scale in a way that seeing an actual life-size model doesn't. That reconstruction toured venues including New York's Grand Central Terminal and the accompanying Smithsonian documentary, Titanoboa, Monster Snake, brought the discovery to a considerably wider audience than academic publication alone typically reaches. Jonathan Bloch's own comparison at the time, directly referencing the fictional oversized snake from the 1997 film Anaconda, and noting that the real Cerrejón specimen dwarfed it, was a deliberate, effective bridge between rigorous science and the kind of pop culture reference point that makes a genuinely abstract size comparison land for a general audience. Vasuki indicus generated a comparable wave of public interest in 2024, helped considerably by its evocative mythological namesake, a serpent king already deeply embedded in South Asian cultural and religious tradition well before the fossil discovery gave the name new scientific weight. That existing cultural resonance meant the discovery traveled through Indian media and international coverage of Indian science more broadly, in a way that a more clinically named species might not have managed nearly as effectively, becoming a genuine point of national scientific pride in India specifically, alongside its more straightforward value as a paleontological find. Neither of these details changes the underlying science, but they do help explain why these two discoveries, out of the steady stream of new fossil species described in academic journals every year, most of which never reach a general audience at all, managed to become genuinely widely known stories rather than staying confined to specialist paleontological literature. Every size estimate discussed so far rests on a fundamental limitation both research teams have been candid about. Nobody has yet found a genuinely complete skeleton of either animal, and that gap is exactly what future fieldwork in both Colombia and India is now aimed at closing. For Titanoboa, ongoing excavation at Tarrajon and nearby sites in the same geological formation continues, driven partly by the recognition that the mine itself, still an active commercial coal operation, represents a genuinely rare window into Paleocene tropical ecosystems that exists almost nowhere else in the fossil record. Every additional field season carries the possibility of turning up more complete vertebral sequences, skull material, which remains particularly sparse for Titanoboa, or even an articulated partial skeleton that could meaningfully narrow the current size range rather than simply reinforcing the existing estimate. Skull remains in particular matter disproportionately here, since jaw and tooth anatomy can reveal detailed information about diet and feeding mechanics that vertebrae alone can't fully capture. And Titanoboa's skull material recovered, so far, remains considerably more fragmentary than its vertebral record. For Vasuki indicus, the situation is, in some ways, even more promising, precisely because the fossil-bearing layer at the Penandro lignite mine is still being actively worked as a commercial mining operation, meaning new rock is continuously being exposed as excavation proceeds. Dada and Bajpai have indicated interest in returning to the site for additional collection work, and given that the original specimen sat unrecognized in a museum drawer for nearly 20 years before anyone realized what it actually was, there's a reasonable possibility that other giant snake material from the same region has already been collected and simply hasn't been properly identified yet, sitting in existing museum collections rather than requiring entirely new fieldwork to locate. That's a detail worth sitting with because it's a genuinely common pattern across paleontology more broadly. Major discoveries don't always come from a shovel breaking new ground. Sometimes they come from someone finally taking a second, more careful look at material that had already been sitting in a drawer for years, initially misidentified simply because nobody working with it at the time had reason to suspect it belonged to something this unusual. Both Titanoboa and Vasuki indicus, in their own ways, are reminders that the fossil record isn't just something waiting to be dug up. A meaningful part of it is likely already sitting in existing collections around the world, waiting for the right question to be asked of it. Taken together, Titanoboa and Vasuki indicus aren't really two isolated curiosities. They're evidence of a genuine repeating pattern. Whenever Earth's climate has run consistently hot enough, and whenever a large ecological gap has opened up at the top of the food chain, reptiles have repeatedly evolved toward genuinely enormous body sizes. Independently in different lineages, on different continents, separated by millions of years and thousands of miles. That pattern matters beyond simple paleontological curiosity. Both animals function as physical, measurable proxies for reconstructing ancient climate conditions, using body size to work backward toward minimum temperature estimates in periods and regions where direct climate data is otherwise difficult to reconstruct. And the underlying relationship between reptile body size and ambient temperature that makes that kind of reconstruction possible is the exact same relationship that leads some researchers to flag long-term climate warming today as a variable worth watching carefully in modern reptile populations, not because giant snakes are likely to reappear anytime soon, that ecological opportunity closed tens of millions of years ago, but because the basic physiological relationship between temperature and cold-blooded body size hasn't changed, even if the surrounding ecosystem has. For now, the title of largest snake ever known remains genuinely contested between two animals separated by roughly 10 million years and half a planet, each reconstructed from a partial skeleton, each pushing the outer edge of what a cold-blooded predator's body can physically support. Somewhere in Colombia and somewhere in India, both stretched out along ancient tropical rivers, comfortably larger than a school bus, comfortably capable of swallowing prey that would seem impossible for a snake to handle today. The fossil record hasn't finished settling which one was actually bigger, and there's a reasonable chance neither Titanoboa nor Vasuki turns out to hold the final word on the matter at all, given how much of both animals' skeletons still hasn't been found,